Welcome back. This is Chem 230 with Dr. Bob Blake at Glendale Community College in Glendale, Arizona. And last time we were talking about building an electron configuration and electron energy diagram for an atom, where you're trying to find where the electrons would go within the atom. And you start with the lowest energy orbital, and you move upwards until you have enough orbitals to accommodate all of the electrons. And so figuring out or remembering the filling order for orbitals is a little difficult because it's not totally intuitive. The fourth energy level starts to fill before the third energy level is done filling. So the 4s sublevel is lower in energy than the 3d, and that's oftentimes a little difficult to remember or work with. But one of the great correspondences in the world is that the periodic table is based on the reactivities of the elements, and the reactivity of the elements is in large part due to where the outer electrons are. So that's one of the reasons we're concerned with the electron configurations, is we want to know where are the outer electrons, in which orbital are they in, how many outer electrons are there, and then what are they going to do when they interact with other atoms. So if you look at the periodic table, there's information in there on where the outer electrons are. And you'll see this often in classes, that the first two columns of the periodic table are often referred to as the S block elements, because the elements in those two columns have outer electrons in the S sublevel. So the S block, the outer electrons are in the S sublevel. So for instance, the simplest atom, hydrogen, has one electron and it sits in the 1s sublevel. If you're following along with that reasoning, then a lot of people will place helium here in the periodic table because its outer electrons are in the S sublevel. So hydrogen is 1s1, helium is 1s2 for 2 electrons in the 1s sublevel. So this row of the S block is often referred to as the 1s row, because the elements in this row of the periodic table have their outer electrons in the 1s sublevel. And that's where, in terms of reactivity, helium certainly belongs here with the noble gases, but in terms of electron configuration it fits nicely in here, because every element in this column has 2 electrons in its outermost s orbital. So if you have 2 electrons to deal with, they both fit in the 1s sublevel. If you get a third electron, you have to go into the 2s sublevel. So when you look at the element numbers, the atomic numbers for the elements, hydrogen is number 1, helium is number 2, right? And then lithium is number 3, lithium. So lithium is going to have a configuration that accommodates 3 electrons. It's going to be 1s2, 2s1, and again you see that if there's outer electrons in an s sublevel, the element is going to appear in this part of the periodic table. Over here, neglecting helium, which again has outer electron in the s sublevel, so for electron configurations we'd put it here, but the 6 columns on the right of the periodic table is referred to as the P block elements, or section of the periodic table, because the elements in this area of the periodic table are going to have their outer electrons in p orbitals. So if you look at, say, carbon, which we did its electron configuration before, 1s2, 2s2, 2p2, carbon is in the p block, so its outer electrons are in p orbitals. And notice there is no 1p sublevel. The first energy level only has s electrons, but the second energy level has s and p, 2s and 2p. So the first time you have an element in the p block, it's going to be in the 2p sublevel. So this is where I'm sort of showing that there's a map on the periodic table to where the orbitals are. because the s block, you have the 1s sublevel, the 2s sublevel, the 3s sublevel, the 4s sublevel, the 5s sublevel, and so on. And if you just look down this column, we can label each row of the periodic table with the energy level of the orbital, and then based on which part of the periodic table it's in, what sublevel orbital designation there is. So if we count down the s block, we have 1s, 2s, 3s, 4s, 5s, 6s, 7s. If we count down the p block, we have to start with the second energy level. So there's no 1p orbitals, but you have 2p, 3p, 4p, 5p, 6p, etc. And if you locate an element in the p block, so I have carbon here, I go down 2 and over 2 more, so going from carbon down 2 and over 2, we get to selenium, Se. You can see it's in the p block, the 2p row, the 3p row. Selenium is in the 4p row of the periodic table, so you'd expect the outermost electrons in selenium to be in the 4p sublevel. So that's where, just looking at an element and its location in the periodic table, I can tell whether its outer electrons are going to be s electrons or p electrons, or if we go to the center part of the periodic table, the d block elements have their outer electrons in the d sublevel. Again, where do we first see d electrons? Not in the first energy level, not in the second energy level, but in order to have a d sublevel, you have to be in at least the third energy level. So you have 3d is the first row of the transition elements, 4d is the second row, 5d is the third row of the d block. So you can see how it follows along. So if I write out a little map here, I've got marked out the specific rows of the s block, the p block, and the d block. Now if I just follow along with the atomic numbers, it'll tell me the filling order for the orbitals. So I start with elements 1 and 2, the 1s, then elements 3 and 4, the 2s. Where is element 5? Element 5 is boron, and that's in the 2p row. So after we get done with 2s, we go to 2p. That brings us through neon. Then after element 10, where do we find element 11? Element 11 is sodium, and that's the 3s. So we go 1s, 2s, 2p, 3s. Then after we get done with 3s, element 12, where is element 13? Aluminum is in the 3p row. So after the 2p and the 3s, right? And sorry about the handcrafted typo there, but we went sodium and magnesium were the 3s after the 3p, and we skip over the d block to the p block and go 3p next. And you might expect the 3d to be right after the 3p and fill up the third energy level, but when we get done with argon and have accounted for 18 electrons and finished off the 3p sublevel, where's element 19? Element 19 is potassium in the 4s. So if we're following along with the atomic numbers, after we get done with the 3p row, elements 13 to 18, we find element 19 in the 4s row. So 4s there. And now we finally get to where I wanted to write this earlier, but we have to wait till now. After we get done with 19 and 20, element 21, scandium, starts the 3d row. So after the 4s goes the 3d, and you can continue to follow along with the atomic numbers. After you get done with 3d, out here is zinc, element 30. Where's number 31? Gallium is the 4p. So after 3d we get to 4p, And if you follow along with the atomic numbers and understand this labeling I've done with 2p, 3p, 4p, 5p, 3d, 4d, 5d, etc., you might ask yourself, when do we have the f orbitals? So there's 14 columns over here. Those are the elements that the outer electrons are in the f sublevel. Remember, the first time we have the f sublevel is in the 4th energy level. So where's the 4f? The first element in the 4f is cerium, Ce, right? And that's element 58. So the 4f will start to fill after element 57. So we look on the periodic table, where the heck is 57? 57 is lanthanum, which is right here. So after you put one electron in the 5d for element 57, then you scoot over to the 4f with cerium, which is element 58. So again, the periodic table gives you sort of a map of the filling order. For this class, being a fundamental organic class, this is about as far as we need to go, and the periodic table can remind us that the 4s sublevel, potassium and calcium, fill before the 3d sublevel with these transition elements. So 1s, 2s, 2p, 3s, 3p, 4s, 3d is a nice ordering of the lower energy sublevels. And again, if you familiarize yourself with the periodic table and the electron configurations, you can see that ordering in the periodic table.